In this video, we will see Prim's algorithm for finding minimum cost spanning tree. So in the previous video already we have learned about spanning tree and the minimum cost spanning tree. So now let us see what does Prim has suggested for finding a minimum cost spanning tree. So for explanation, I have taken a weighted non-directed graph and it is connected graph. All the vertices are connected. So yes, we can find a spanning tree or minimum cost spanning tree. Now let us learn the procedure given by Prim's. So Prim's algorithm. Let us learn it step by step. So the very first step, Prim says that select a minimum cost edge from the graph. The minimum cost out of all these edges is 1, 6, 1 to 6. So first select that one. So this is selected. Now follow the steps very carefully. Next step is repeating step. So always we will be performing same thing. So let us see what is that repeating step. Now from the graph, select a minimum cost edge, next minimum cost edge, but it must be connected to already selected vertices. Selected vertices are 1 and 6. So it should be connected to those selected vertices. So if I look into the graph, the minimum one is this one. And next is this one, next is this one. No, don't say take those edges. Select the one which is connected. So for one, connected one is this one, which is of 25. And for sixth, connected one is this one, that is 18. So select this one, 18, that is 6 to 5. So next edge is 6 to 5, 18. Now repeat the same thing. Select the minimum but connected. So from 1 it is 25, from 5, 16, 12 and 11. So 12 is minimum. So select 12. Now next, from 1, 6, 5 and 4, find out the minimum connected. This is 25, this is 16. For this one, this is 11 and this is 10. So 10 is minimum. Take that minimum. This is 3 to 4 or 4 to 3, which is of weight 10. Now the selected vertices are 1, 6, 5, 4, 3. We have to select the minimum one which is connected to any one of these. So from 1 it is 25, this is 16 and this is 11, and from here 9 is there. So okay, select that as minimum. So 2 and it is 9, weight is 9. Then the next minimum is 2 to 7, that is connected to 2. Connected to 2. 6. Yes. So what is the total cost? 5 plus 18 plus 12 plus 10, 9 and 6, 60. So the total cost is 60. So this is a minimum cost spanning tree suggested by Prim's. We have followed the algorithm and we got the minimum cost spanning tree. Now the question is why he said that it must be connected. See, we have to achieve two things. First is it must be a spanning tree. So tree will be connected and it will not have cycles. Yes. Second thing is we want minimum. So the first preference is it should be connected so that it's a tree. So if I look at the steps that I have performed, so first I selected this, then this one. Up to here if you see it's a tree only, connected only. The next connected. So if you stop in between also, if you perform few steps and stop, if you don't complete, still you get a tree only. So that is the reason Prim has suggested focus on tree, try to maintain it as a tree, right? Then check for a minimum edge. So this is how Prim's algorithm works. Now let us do some analysis on Prim's algorithm. How much time it is taking? See, what is the work we are doing here? We are generating n-1 edges and forming a spanning tree. We are scanning through and selecting n-1 edges. So this is definitely v-1. This is v-1, n-1. So n-1 edges we are selecting. And every time we are checking the connected one and finding minimum out of the connected edges. So how much time it will take for finding the minimum edge? So let us say maximum we are checking all edges and from there we are selecting minimum connected edges. So the number of edges are E. So the time taken by Prim's algorithm is V into E. V is number of vertices and E is number of edges. This is also linear, this is also linear. So we can say this is n into n, that is n square. So we can say this one n into n square. So the time taken by Prim's algorithm is n square. Then if you are using some heap data structure for finding minimum edge from the set of edges, then the time can be reduced to number of vertices minus 1 into log e edges. So if you see, this is linear n and this is logarithmic, so we can say log n. So the time complexity of Prim's algorithm will be n log n if a faster method is used for finding a minimum cost edge. Like we can use a heap or red black tree for finding minimum edge. Then one more thing about Prim's algorithm. See, if I have a graph which is not a connected graph, if it is not a connected graph, this is a non-connected graph. If I run Prim's algorithm on this one, then it will start from this minimum cost edge and it will try to select the next connected and next connected, so it will never reach on the second component because it is not connected. Yes, we already know that for a non-connected graph we cannot find a spanning tree at all. But what happens if I run Prim's algorithm on this one? So Prim's algorithm may find out a minimum cost spanning tree for one of the component. One of the component it can find out. Because they are not connected, it will never reach on the second component. So that's all. This is the analysis of Prim's algorithm. Next, we will look at a program on Prim's algorithm for finding minimum cost spanning tree.